this is Bauble. It's a playground for producing 3D shapes and animations using a programming language called Janet. You write a little script, it compiles it to a GLSL shader, and then it has a little renderer that will execute that shader for you. So it's kind of like a shader toy alternative, except you're writing in this high-level language, and it's really, really optimized for SDFs. It has this built-in library of SDF primitives, so you don't need to implement your own Boolean operations. You could just use the default subtract, as we're doing here. And this is a little demo, and I want to just go through all of the new features of Bauble. Bauble's been around for a while, but I recently rewrote it pretty much from scratch. A lot of the UI is the same, but the core compiler is completely different. It's way more powerful and flexible, and I want to highlight some of the exciting new features. So let's reset. We have a simple ball. The first and probably biggest, most exciting thing is that Bauble supports 2D STFs now. And this might seem like less impressive than 3D, but it's actually really nice, in no small part because you can turn 2D STFs into 3D STFs. So you could define a cylinder as the extrusion of a circle. But we're not going to do that right now. I just want to focus on 2D. So all of the combinators and things that you're used to from the existing Bauble that you've never used still exist and work in 2D. But in 2D, you can see the entire distance field at once. So you have this visualization of the iso surface. And this can be really useful because although this is already a 2D thing, imagine that we have the 3D version of this shape. And we want to say smoothly union these. Oops, smoothly union these together. So we have this smooth shape. And I want to say, what does the interior distance field of this look like? Well, I can't really answer that in 3D. I have these debug views that kind of give me an idea of how the distance field is behaving. I can see that it looks like it's a pretty good distance field. But let's say that I change this. I want this to be ball like 50, 100. So, picked a bad axis for that. I know that this ellipsoid shape is not actually an accurate SDF. It's only an approximation. So you might be curious, like, what does the distance field of this look like? How bad is the approximation? And what do I need to think about when I'm using it in like smooth union operations or Booleans, other things? If I'm using this as a subtraction, what's the result look like? Well, we can answer this now by just slicing into the shape. So I'll slice it along the x-axis or the z-axis. And I can see now the interior distance field of my three-dimensional shape. And this is really nice if you're working with something that's like quite weird. Like the less spherical your ellipsoids get, the worse their distance fields become. And it might actually start to matter to you. Like see here, that's maybe not, that's okay. If I increase this rounding radius though, you can see this, it's kind of hard to visualize. So I'll just add a color, maybe like that's a terrible color. You can see that weird kind of hump creeping in, and that's strange because I would expect it to be the opposite. But if you look at the way that the distance field behaves just for the ellipsoid, you can see that outside of the shape itself, it has this strange humpiness to it. So it's useful for debugging. Like, wait, why did my shape look like that? Why do I have this little divot here? It's just a nice way to like get a better understanding of sine distance functions. Another thing that it's useful for is say that this is actually an intersection. I can see that, whoa, I produced like actually a pretty bad distance field there, possibly because it was so rounded. And that's something that might be kind of hard to tell if you're just looking at the final result. So 2D SDFs. That's the basics, but let's go back to something. Make a big circle. So we saw that we can extrude these along some axis, along different axes. We can also make solids of revolution, which is really fun. So this is just what a torus is. It's a circle that has been revolved around some axis. And then operations that we apply in 2D say that we take the shell of the circle to get this like thin disk, and then we could extrude that, and now we have like a hollow cylinder, which is not a 3D primitive that we otherwise have, so that can be useful. 2D shapes also work with things like tiling. I can tile the plane, And I think it's a really good way to visualize and understand the behavior of the tiling. I'll make this really big. The tiling distance fields and like why you run into problems when you're using domain repetition with uneven shapes. If I then make this a box that I rotate, a rect in 2D that I rotate, you can see that like actually this is not a very good distance field. And if you're doing the equivalent of this in 3D, which I'll say we'll rotate along the y-axis, this is kind of symmetric, but you can see that these artifacts start to appear because you're not ray marching like a very good distance field. And I guess I could show you that more directly by slicing it back into 2D. You can see that sometimes this like peeks out of its shape, and these sharp discontinuities in the distance field at the corners, this is like going to give you trouble as soon as you start ray marching it. So, well, I guess I can highlight something that Bauble can do now, which is kind of exciting, which is we now have this oversampled repetition, and this allows you to have asymmetric shapes when you're using domain repetition and ray march them, essentially looking at the adjacent shapes to compute a better distance field. And let's see how this looks in 3D. Whoops. Infinite rotating cubes that are all being ray marched with none of the artifacts that we were seeing before, which is pretty exciting. Okay, that's kind of cool. Another one that we got, let's just go here. We have custom cameras. So this is something that you couldn't do before, which made it hard to art direct a scene. You can like rotate, obviously, and have this orbital thing. But now you can just set this variable called camera. And there's two types of cameras, perspective and orthographic. So I'll just highlight what you probably expect. So perspective camera at 500, 500, 500. And then we have to look at the explicit camera. And then we have different operations for camera. Zoom in. I can vary this smoothly, zoom in and out. I can tilt by different angles. It's really coarse. These are radians. Tilt, pan, all the operations that you expect. I can also move the camera, which is like a little bit confusing because it's at a weird angle, but it's the thing you expect. I can move, I can rotate the camera directly instead of using the look, relative, tilt, and pan operations. I can also create an orthographic camera, which is kind of nice. I'll go back to our tiling example. I tile, I think I want a box 50, tiled 150, 0, 150, with an orthographic projection. Don't zoom less than 0. You can see that it's, you get this isometric effect when you position the camera in an isometric position like this, but you can also use this to create kind of neat, well, to make it a little bit farther away, and it's clipping at the near plane, but this is pretty nice. And unless you like more easily art direct a scene or make something that looks good from a specific angle without you having to like find the angle that you want to view it at. Custom cameras, you can also change the background. This is not maybe super exciting, but something that is kind of exciting is you can change it to transparent. I'm using dark mode right now, so you can't, it's not all that different, but if you were embedding this on a page or something, you can, you don't have to render the whole opaque canvas. You can just render the background to be transparent. It's also just a name for that color. But you could also use this to do like kind of fun expressions. So we could look at frag chord y frag chord and just 0 or something. Frag chord remap plus. I'm just gonna take that out so we have no shape. That's beautiful. So frag chord's going from -0.5 to 0.5, so multiply by 2. We get this kind of like classic OpenGL example. Let's not do that. We have various notational improvements, which I've kind of been casually using. I'll highlight another new feature in Bauble. So in old Bauble, when you used a rotation, you specify an axis as like the cardinal axes X, Y, Z as keywords like this. and that's no longer the case. Now you actually pass a unit vector, and there is a vector called x, which is just the same as saying, the x unit vector. But you could pass other vectors as long as they're normalized. So any normal vector will work as the axis of rotation. So I'll take this, or this is a good one. This is just with the default view pointing straight towards the camera. But I have to normalize that. And I don't like, anytime I have like multiple closed parens nested like this, it's just hard for me. I don't want to have to think like that. So there's a new way that you can write this, which is like that. So pipe works inside brackets like this. And so do other operations. Like if I wanted to, I don't know, add, like this and then normalize that, I get this kind of off-kilter axis because I'm still normalizing it. So binary operations and pipe notation just applies to everything in the vector, and it's the same as if I'd put the square brackets there, wrapped it in round parens, and then normalized. In addition to rotating around arbitrary axes, you can also, I'll use a cone now because I think this will be a better example, but I can say like align this cone where y was previously, align what was y to now be the vector 1, 1, 1, normalize, and now I have a cone that is pointing like basically towards the camera. If I maybe union this with a box frame 101, kind of see it's like pointing towards that camera now, and as I give it different vectors to align to, it's gonna do that. And maybe I can start this over, and this is useful if just you're making an animation or something and you want something pointing at something else, like an eye following a target or something. Those are our rotation improvements. Talk now about, there's much improved lighting and ambient occlusion. It's not this like weird special cased thing that it was before, so let's make this, and we'll shade this like blue. We'll shade this like, do I have like an aqua color? I want like 0.1, 0.5. It's kind of a nice color. So make this sphere a little bit bigger so we can actually see it. Okay, so this is a shape. And by default, we have a little bit of ambient occlusion, but I'm just gonna make my own lights. So I'll say with lights, I'll start with an ambient light. It's like pretty bright. And I'll say that it's just sitting slightly away from every surface. So we get this little bit of specular highlight. I think it looks kind of neat. And then I will add a directional light. Or no, let's just do ambient occlusion. So I'll say the brightness of this light, let's just make it full brightness. The brightness of this light is, by just saying occlusion, I get the default parameters, and this is what Bauble used before, and this was the only occlusion that you could use, but occlusion has different arguments that I can use to get a higher quality and a more like art directable thing. So I'll say that I want the distance of this to be 50, so I get this more soft spread out. I'm not sure how well this is going to come through in the compression. So I will pick a cylinder that is like 50 and 200. That's a little better. You can see the ambient occlusion. So distance of 20, 10, I can like change this and get a more intense effect. I can also say that the direction of the occlusion is like, give me like a random vec3 based on the current point, and add that to the normal, and then normalize the result. So now, instead of just, by default, the ambient occlusion rays are going to go away from the normal. And this can give you, it looks fine here, but this can give you kind of weird results when you have a shape that has like a banded neck like this. So I'll just remove this for a second. You can see that the normal around the middle of this neck didn't actually think it was occluded because it shot rays that went like perfectly out. It just happened to hit. So it's like, oh, there's nothing around me, I'm fine. And this is a problem with the just very coarse ambient occlusion that we use. So you can add a little bit of jitter and noise hash maybe minus 0.5 so that it's a little more distinct, and it still looks terrible, but it's like a little bit better. And then you could also set the anti-aliasing. Sorry, this is changing, but right now it's AA grid size. You can only have this kind of rectangular grid anti-aliasing, but I'm gonna make this support custom samples soon. So you can use this to like kind of get away from that noise artifact that we introduced intentionally. Lights are also much better, but I'm not going to go completely into that. There's helpers. Ultimately, it's still the same that it was. There's only really a point light is the only primitive, but you can, it has built-in helpers for constructing ambient directional lights from point lights. So the default is still like ambient light and then with some occlusion and a directional light that's kind of far away. Looks fine. I think I should probably increase the default occlusion step, but whatever. Okay. Let's talk now about the GLSL escape hatch. This is pretty exciting. So say that let's just take R2 and color it red. So this is saying I have a 2D shape. This is just the entire 2D plane. And I'm going to write a color, but that's not a very good color. So I'll say I'm going to write black and white Perlin noise of Q with a period of 20. And that doesn't look amazing. I don't know. There's this helper now for FPM. So this is take, 4 iterations of Perlin noise. And maybe, that looks kind of, I'm not saying this looks good, but it is an example. This lets you create much more like intricate, detailed patterns. You kind of get these cloud effects. But FPM, you have some control over it. You can provide a custom function for how we're gonna like get a new point each time. So by default, it would just be double it. But we could say, like double it and then rotate it by some factor. And then we balance our parentheses and maybe, I don't know, maybe this gives us an interesting kind of shape. As I vary this, it's kind of cool. Play. Maybe, I don't know. But maybe, even though you have some control over FPM, we can actually just write our own FPM now. So I'm going to say GL do, and just like Janet's do gives you a series of statements or expressions and gives you a single expression back, GL do does the same thing, except we're now using this macro, and we're just writing GLSL code directly. And it's a little weird, it's not super documented, but I'll just show you like broadly. I want to make a local variable that shadows the dynamic variable q, which is the point in 2D space that we're looking at, and I can say for var I is 0. This is how you declare an integer in Janet, so the int 0, and I less than the int 4 plus I, and this is like a GLSL for loop. We'll say var result starts at 0, and plus equals result Perlin Q. I think 20 is fine. Then we'll say times equals Q2. And we'll have an amplitude that starts at 1 that we will half each time. So times equals A 0.5. And I will return result here. So I did my own version of FPM just now. It's not identical to what I was doing before. I picked a different period, probably, and not as many steps. But you could use this if you wanted to, like, not, for example, have the amplitude decay exponentially like this. You could say maybe we just want the amplitude to be like a little bit smaller each time. And this, I don't know, we're kind of not really making FPM anymore, but gives you an idea of the, I'm not actually using the amplitude, that's why it looks so bad. Okay. back to where we were, you can see that, yep, same result. And now let's just linearly step the amplitude down each time instead of having that. So I don't know, you can use this to do different effects. But the point is you can just write arbitrary GLSL. You don't need to, do it like this either. You can just say, like take frag chord and like do your gamma adjustment and like just write your main function entirely and forgo SDFs and like don't use any of the Bauble helpers if you want. Something that you can use this to do is make your own custom shapes. So I'll say GLDo, and this is like a silly example, but length p minus 100, like that's actually the SDF for a sphere. I didn't need to use GLDo. I didn't actually end up writing any custom GLSL, but imagine that I'll say, I don't know, foo is length of p, and then I want to return foo times foo minus 100 times 100 and take the square root of the result. Maybe that gives me like something kind of interesting. No, that's useless. I don't know. You can do it. You can write arbitrary expressions for distance fields. Great. Interior color fields are something that this is something that always really bothered me. Actually, let's look at it in 2D. So I'm gonna make a blue circle, and then I'm going to union a red box, or maybe an orange looks good. Maybe no, red. Okay. So this already demonstrates the feature that I want to show off, but maybe you can't exactly tell. So let's jump back to 3D. Okay. I guess I'll shade these instead of giving them a flat color so you can see a little bit better. Okay. So what I'm going to do is now look inside the distance field. So I'll intersect this with the plane in the z direction. So you can see that this is like what you'd expect. And I'm only calling this out because in old Bauble, this was not what you expected. It worked in the following stranger way, which is sometimes useful, but it would basically say, okay, well, when you have an interior distance field, the color at this point is the color of whichever surface is closer to that point. And that's maybe not what you expect. It is symmetric. So if you write like union of this ball and this box, it doesn't matter what order these show up in. And that is not true of the like other way, where here we're saying, oh, well, the ball actually like sits on top of the sphere, which is completely intuitive, especially in 2D. It's what you'd expect. Shade becomes color again. This becomes a circle. This is what you'd expect. I can say put a rect on a circle or put a circle on a rect, and they do different things. But it never worked properly in 3D, and now it does, which is exciting, especially if you're using this to do like painting, using it to take one surface and apply its color field to another surface, which is something that you might want to do if you have like, I want a box, I'm going to shade it white, and then I want to union, what's a good shape? Like a star that's like 50-30, extrude in the z-axis by some amount. You can't see the shape. And I'll take that and I will shade it red. And now I only actually want to union this color. So I'll take this shape and I'll say color, well, yeah, we'll use this sphere. It doesn't have to be the same shape at all. Color this sphere with this other shape. And now I have the interior distance field of that copied onto this sphere. We could, of course, just use a box. And This just didn't work in Bauble before because of the way that it was doing the unioning. You get these, weird kind of results depending on the particular shape of the interior distance field that you had given it. So now it works. And that's giving me the smooth kind of fuzzy painted thing, which you can see here matches that smooth boundary that we were seeing before. Maybe this is more clear if I take a box that is not quite as deep. So 150. I really meant to do that on this one. Guess how many times I've rehearsed this video? I have not. Yeah, so we were using this, basically this is how old Bauble would behave. It's like, while you're close to the surface of the star, you'll get the good distance field, but the actual interior distances are not. And mostly the reason why we still have both is it's really useful in different operations. So if I'm, go back here, instead of union, pretend like I'm subtracting. So this is actually what I want now. I want to say, well, the color is whatever is closest because the ball's not there anymore. So if I use this rounding thing and say, okay, now do the smooth subtraction, you can see that there's no more blue. It's immediately purple because the blue isn't part of the shape. So we're only seeing where the blue bleeds out into the box around it. And that looks really bad. So the old way that Bauble was doing looks much better when you're doing these smooth Boolean operations because you mostly care about what the surface looks like. You don't actually care about the interior distance fields. But if you were to then like look at the intersection here, maybe along the Y, you can see that that's not probably what you would expect it to look like. You might expect it to look something more like that, but yeah, it doesn't. And you could, subtract a larger ball and use that for the color field and then use the smaller ball for the distance field, but you don't have to do that. Okay. That's interior color fields. And then I just wanted to highlight, this is like, I think a pretty neat shape that I've used in lots of demos. So when we're morphing between two distance fields, we can give this some amount to like go between them. And when this is in the range 0 to 1, you get totally reasonable results. But when you get outside of this range, this is way too big, then you get these kind of silly, weird results. But it looks good still. Like this looks like we just constructed a pretty complicated distance field with a very simple expression. But it's not actually a very good distance field. And we can see that if we look at the debug views. We can see that it's not exact. Or if we say slice it along the y-axis, I'm going to say oscillate t every 5 seconds from -50 to 50. And if I press play, this will just like scan the shape for me. And you can see that, different parts of space are distorted in different ways, and the distance field is not exact. So, fine. This has implications. I'm going to look at old Bauble now just to compare. So this is this same shape, but we've put a blend fog shader of red on it. And you can see it looks awful. And it looks awful because there are a lot of points where the rays that we're ray marching are actually penetrating the shape. They're landing inside of the shape. And this, if we're not shading it, still looks fine because the normal is the same on the surface or like just below the surface. But then when we try to cast lights to it, we say, well, no light reaches this point because it's inside the shape. It's in the shadow. It's casting a shadow on its own interior self. And that's like quite silly. So when you're doing anything at all with not perfectly exact distance fields, you have to use the slow combinator to like slow down the entire ray march so that it doesn't penetrate shapes and get through the surface. And you can see, looking at this view, no more magenta means that we succeeded. In new Bauble, this is like much less necessary. It's still sometimes necessary, but it's less necessary much less often. So you can see the different default lights in old Bauble and new Bauble. Still kind of playing with the lights, but this all the shading looks good, even with no slow factor. And this is because the new ray marcher is just smarter. And when it penetrates a shape, it will like try with not forever, but it will like say, oh, what if I like sneak back a little? Like what if I go back and try to find a point very near the surface instead of saying, oh yeah, well, I'm through, so I'm going to stop. We'll like back off a little bit. And this improves your ability to ray march like funky shapes really well. Funky shapes like expand by Perlin noise, like give it a size. Expand by Perlin noise by, I don't know, times 10. Like this is a pretty funky shape. Not at all a correct distance field, not even close. An old Bauble, we had to explicitly divide the period, and to expand was called offset, and ball was called sphere. Okay, so this is an example. You can see all these places where it's failing to actually hit the surface, and it's doing much, much better with the exact same shape in new Bauble. You want it to be cyan. You don't want it to be black or purple. I know this doesn't really mean anything to you, but it's a good improvement. Okay. So I already showed you multi-sampled repetition, but I want to show it again because I have a kind of cute demo. So I'm going to take this and I'm going to tile it, and I'm going to say 150, and I'm going to limit it. So only like 5 repetitions. This is way too big of a tile. Okay. So I can do this. And now as soon as I have anything that's like slightly asymmetric, well, first, we can vary this, of course, in the same way that we could in old Bauble, just a nicer API for it. So we could say like HSV, give me just a random value based on the current coordinate, and I think like slightly less saturated looks a little bit better. Shade it. So I have these random balls. And I can also, in addition to like coloring them distinctly, I can also distort or move them distinctly. Or I could say like a sphere, give me morph between a sphere and a ball by an amount that varies by the thing that the current coordinate that you're looking at. And that didn't work at all. It's not what I expected. Hash of I. It's giving me what oh, because he said sphere. Gosh. Cool. Box and a ball. That's what I meant. So we can have different shapes. And we can also like move these. So I'm going to say move each one by random vec3. And that's going to be random numbers from in the range 0 to 1. So I'm going to subtract 0.5, multiply by 2 to get numbers in the range -1 to 1. And I'm going to then say, well, like 25, like pretty big. And I got garbage right away. Like this is no longer visible. And if we look at the slice on the y-axis, and I can't render it, I'm going to go to this new debug view, which is show me the default color. So show me the isosurfaces. You can see why. Like this is nonsensical. So we have to use oversampled repetition here. And it's still not even like totally good, I think. We want to say like sample from -1, sample to 1. And the default is to sample from 0 to 1. And it basically means like use directionality to decide what direction we're looking at. I know that didn't make sense. If you've used domain repetition, I think the operation that we're doing makes sense. But anyway, this lets us have this really offset, off-kilter distance field. And I'm just going to take these back to being balls. I don't need to morph them. So I have this random array of balls. And at like a pretty cheap cost. I limited this, but that was just so we could see it all. But like we could, have 100 of these and still ray march it. It's not, it got slower, but not a million times slower. So I have these. And then the thing that I want to do is show like a cool, just the new compiler has a better representation and like a first-class representation of these things. So this is a shape type, and we can say, well, give me the shape's distance field. And that's going to give me a float at any point that I ask it about. So I could say, like, take a ball, and then I'm going to color the ball with a vec3 of this other shape's distance field. And what did that do? That did absolutely nothing. It's like it ignored me completely. It's kind of weird. Did I break this? I must have gotten into an infinite loop somewhere along the way. Not sure exactly what happened there. Still new, beta, warning. Okay, so you can see that a lot of the time the distance is like exceeding 1 and it's clipping. So that's not like a super good example, but here's a more interesting example. Instead of coloring it, I could just expand it by an amount that varies by the distance field. And now I have this kind of 3D Voronoi-like cellular noise. And these values are really like big and small. So let's change these to like 10 times 5 and limit maybe 100. Okay, so this is essentially like cellular noise. I know it doesn't look very good. It's only one iteration of it, but we kind of just computed this without actually writing cellular noise. Like we just wrote the definition of it, which is like tile a point at random positions in space and then find the distance to the nearest point, and you have this. I think it's really neat. And then Bauble actually has, like, you don't have to write this. Ooh, I made it really weird. You don't have to write this because we have just a built-in cellular noise. You can just say Worley of P with a period of 10 or 20 or something, and multiply that by 10 so we can see it. This is a built-in, but it's cool that you can define it in this way so easily because you can use this to, you can do the fast approximation as well, which doesn't really hurt us at this point. We could say, well, what if we didn't have a ball? What if we actually had like a box? Like, what is that? We sort of made this kind of cellular geometric thing now. And maybe we do want the good samples. And we can use this, this could be anything. What happens if this is a cone? We get these like interesting alternate shape distortions. And look, we made something kind of pine cone-like. I don't know, it's like an interesting texture. And none of this was possible before because everything was very specific, hard-coded, like, here are the shapes, you can have these compositions and primitives, and now Bauble is really like a completely general GLSL compiler. So those are a lot of the new features. Gosh, there's more that we could talk about. Like you could have this shade red, you now have this bump operation. So you can say like, okay, distort the normal field of the shape by noise. And this is different from saying expand the shape by noise, which of course you can still do. I think this is maybe a more accurate simulacrum. So this is slow because every step of the ray march you have to evaluate the noise. And we have this expound operator, which gives you like it puts a bound around the shape to reduce the cost of evaluating this very expensive noise. But when you use bump, it just says, okay, like ray march this perfect sphere, and as soon as you hit the surface, pretend like the normal contained this extra bit of noise, but the shape itself didn't. And it lets you add like textures much more cheaply than you could do in old Bauble, and the only operation you had was this expansion offset operation. You can alter normals, and this comes down to like, this is a representation of a shape as a bunch of distance, a bunch of fields, distance field, color field. You can represent a normal field and have analytic normals. We don't actually do that in Bauble. That's kind of like the eventual idea, is you can have shapes with analytic normals instead of doing the tetrahedron approximation. And this, you often introduce like high frequency noise when you're doing this. And then if you set a grid size, you can make like much better looking samples. I don't know, we could bump this like slightly more. That looks terrible. Anyway, That's all, I guess, the new features. Actually, I want to show off my favorite feature. This is still a work in progress, so don't um, judge too hard. But I'm really excited about this because it's an effect that I saw in Inigo Quiles' Selfie Girl video, and ever since then I've just wanted to be able to do it. And oh my gosh, I keep like mixing up ball and box. Not great. Okay, so here's a subtracted, um, Boolean operation. Simple. What we can do now is extrude this along a Bezier curve. So this is, I think, really exciting. So I'll say like, we'll start at 0, 0, 0. Our control point will be like 100, 100, 0. And then maybe like 200, 0, 0. Let's give that like way more. 500 to 1,000, I guess. Okay. Yes, I should have done this symmetrically. To 0. Okay, so we've extruded this. And just like with tile and stuff, there's this colon version that gives you a variable. And in this case, this is the parameterization of the curve, like how far along the curve you are. And you can use this to say, okay, I want to rotate along the x-axis by I times tau. Not x-axis. Z-axis? Yeah. And that's pretty cool. You can do this like twisty effect. Or, anything else. We could say color this by HSV of I 0.6 to 1, and like have a rainbow that changes along the curve. And then you could also change how much we're doing this. So from every 5 seconds from 0.1 to 1, oscillate by t. And yeah, that's kind of neat. And the specific thing that Achilles uses this for is a 2D extrusion, which we also support. So I'll say radial, I'll give that the name I, and I'll take 3 of these at a distance of 10 maybe. And I'm going to color each one by HSV of I over 6. So I have 3 circles of different sizes, and then I will rotate this. This is still a 2D shape, so I don't need the axis anymore. So I'll rotate this by the new value of I times tau times 2 times 3. And this is essentially the effect that he uses to create the braids and extrude the braids in the Selfie Girl video. Now it's, a few lines of code instead of being, I don't know, it took me a long time to understand the Bezier curve extrusion. And yeah, just wanted to throw that off. There's still kind of a bug that you get into if you're using normals. It's not actually computing the normals on the Bezier curve correctly. I think I might have an idea how to fix it, but yeah, you can see at some points. This is because it's a piecewise function, and around the points, it's really discontinuous. So when we try to approximate the derivative, it's like, I don't know. Okay, very quickly, you already saw I've been doing this the whole time, but we have autocomplete now with all the docs. So almost everything is documented with examples and like descriptions, but mostly this is just nice to see what arguments are available in what order for different functions. And all of the autocomplete docs are also just in one page, so I can go to the reference and I can see here's everything available in Bauble. And I spent a kind of unrealistic amount of time going through and making examples of not quite everything, but most things in Bauble. So it's maybe, even if you're not going to use Bauble, kind of fun to just peruse and see like what types of things you can do with sign distance functions. You can see examples of my Bezier extrusion that I was showing you, and ways to do this with like a stretching effect instead of the expanding effect. Shows all the different operations. There's a better example of the solid of revolution of a 2D shape that we had. Interior distance fields, the different noise functions available to you. So see our whirly noise that we kind of demoed. All the camera operations. Yeah, obviously you can look at this page, but something kind of exciting about it is Each operation has the source button, so you can click on it and it'll take you right to GitHub, and you can view the source. So if you want to like add a better example, if you're unclear about something, you can just jump right into the source and see it, which is kind of neat. The studio itself, this UI that we're using, I showed you this new feature, which is just show me the default surface. Don't show me like the shading or anything. And this is useful if you're working on a scene that's kind of expensive. This is like, give me the quick render. Like, don't calculate all the textures and do all the shadow casting and stuff. Just use the default normal visualization that you were using before. And the camera view, obviously. I think maybe a more exciting thing, this is asynchronous now. The whole evaluation. So this lets us do things like interactively edit, even though this is taking like quite a while to recompile. You can see down here, the new Bauble is much slower than the old Bauble. It's doing a lot more. And this took us like, I don't know, 70 something, 80 milliseconds to recompile, generate the GLSL, recompile the shader. But we're able to edit the value still in 60 FPS, full real time. And that's because all of Bauble now takes place asynchronously, the compilation, the rendering. So even though it's jittery to show up, it doesn't affect your ability to like type really fast, which is cool. Very useful, very nice. And also means there's a kind of awkward thing about old Bauble where if you got into an infinite loop or made a mistake, certain classes of mistakes, you just like brick Bauble. And then if you got really unlucky and we'd already saved the script, then when you refreshed, it would still be broken. And now, you can just edit still. Even though the worker thread is totally locked in an infinite loop now, which has no actual way to break out of it, you can just refresh the page, and we're back. And you can still edit and stuff while the infinite while loop was executing in the background. And that just makes all of this way better. Then finally, this, you haven't used Bauble, so this hasn't bothered you, but one of the most annoying things about Bauble, old Bauble, is, say I want to edit this interactively. Oop, I'm not rendering that. I'm editing this interactively, right? And then I go to undo, and it's like, okay, undo one piece of mouse movement at a time. And it was really annoying. It basically meant that every time you edited a value with your mouse by using the control, click, and drag, you'd like lose all your undo history. It was really annoying. And now in new Bauble, you don't. It batches it. So it's just like you can freely, without fear, edit things with your mouse without losing undo history. And then another just straightforward, obvious improvement over old Bauble is this used to be, I'll say rotate around the y-axis by t. So these are actually all perspective cameras, which is really dumb. Obviously, these should be orthographic cameras in the quad view. You're looking at it like from the top, from the front, from the side. But they weren't because Bauble didn't have orthographic cameras, and it does now. So if we do the same thing, and we look in the side view, you can see that, yes, we have the orthographic view of this. And it just makes it way more useful if you're using this to change where you're looking. Say I want to like zoom in on this side. It's like, oh, actually, that side is like a well-defined concept in all views because the perspective isn't like throwing it off and making it really difficult to see. So that's a big improvement. Lastly, I know this is really long. I guess there were a lot of changes. You don't have to use the Bauble Studio API anymore. We now have just this, which is the Bauble command line. So I've made this very simple. I'm just going to copy it. This is a very simple demo. This was like a classic Bauble demo that I had used in the tutorial before. Two toruses smoothly unioned with one another. Say I want to take this shape and I can, I have this Bauble command line. So I can say, okay, render, and I'll say torus.png. I don't remember all the arguments here. Resolution, and say I want to make like a really, high resolution, good looking video, but, sorry, image, not video. I want to say like, okay, render this in 64 passes. So slice it into 8 different recs in the X and Y direction, and render it at time 0. It doesn't have an animation, so it doesn't matter. I can do this, and instead of using WebGL, this is just using raw OpenGL. I probably don't need 64 of these. I'm gonna say 4x4. And it's, gosh, sorry. It's reading from standard in because I didn't give it the file name, demo.janet. So now I have this. You can use this for anti-aliasing. You can use this to do a really expensive render at a high resolution with high anti-aliasing that you might not be able to do in real time in Bauble.studio. But the more exciting thing that you can do from the command line is this. So I'll say size, I think is like 120, and slices, I'll say I want a 32 by 32. Now if I look over here, I've created a 3D mesh of my shape, and this uses marching cubes. It's not very sophisticated. There's certainly better ways that you can convert an STF into a mesh, but it also doesn't include like normals, it doesn't include color information, it doesn't export a texture and do UV mapping, which are all things that it could do. I could add at some point if I ever have time to work on it again, but right now you just get this simple mesh, which you can then use for 3D printing, and that's not probably good enough for 3D printing, but if we do a slightly higher resolution, maybe, I don't know, you can, have this sit. Obviously it gets much slower as the count goes up, but you can sit this overnight and generate a really high resolution mesh, and then 3D print a really high resolution image out of this. And I've done this. I'll include a link to an example that I made of a cast bronze bauble that I had 3D printed. I haven't done this really a ton, but it's cool to know that you can. Anything that you make in Bauble, you can export as a mesh, and maybe one day a textured mesh as well. And that's the Bauble command line, and you can use Bauble entirely offline from the command line if you want to. I think that the interactive editing and being able to do stuff like this is the way that I want to be interacting with it, but if you want to use Emacs or something, you can do that. And that's all the new features of Bauble. I mean, it's not. There's a ton of new features, and you can see them all on the help page, but I really should not keep blabbing because I could talk about this all day. So check it out. Bauble.studio. All of this is out now. Tons of new improvements that I would love to add if I ever find the time, but it's already pretty fun to play with.